All right, quiz 3 solutions. Only 2 problems on this quiz. That's the good news. The bad news is they're both pretty long problems. So I broke them up onto 2 separate pages. This first problem was meant to be a lot like the written problem for this week. We're supposed to determine the area underneath this curve between these bounds by evaluating a limit of sums. So kind of the long, annoying way. And I think the easiest way to do this is just kind of going through the same formulas. Delta x is always b minus a over n. In this case, a is 2 and b is 3. So I got 3 minus 2 over n, in other words, just 1 over n. And then xi is equal to a plus I delta x. And in this case, a is 2, and then delta x we just figured out was 1 over n. So I got 2 plus 1 over n times I, or I over n for xi. And so to figure out the area under the curve from 2 to 3 of x squared minus x, what I have to do is take the limit as n approaches infinity of either Rn or Ln. I always use Rn so that the limits of my sigma notation match up with these guys. And Rn is the sum from I equals 1 to n of all these different rectangles. The areas of the rectangles are delta x times the height of the rectangles, which is f of xi. So delta x times f of this guy. Since f of x is x squared minus x, what I can do is take this guy, 2 plus I over n, and square that, and then subtract 2 plus I over n. Maybe you can kind of see the x squared here minus the x here. So this is really trying to follow the same beats that we had on that written problem. Just instead of x cubed minus x squared, it's x squared minus x. And instead of from 1 to 5, it's 2 to 3 to kind of keep the numbers a little bit smaller for the sake of a quiz. So how do we evaluate this thing? Well, we got to get rid of the parentheses. It's not too bad because we don't have any cubics here. We just need to square this thing out. So 2 plus I over n squared, 2 times 2 is 4. 2 times I over n is 2I over n, but then the O and the I in FOIL produce 2 of those guys. So I have 2I over n's. So I got 4I over n. And then I over n times I over n gives me I squared over n squared. And then from that I need to subtract, let's leave the parentheses in here for now, 2 plus I over n. So now I can go and combine like terms. 4 minus 2 is just 2. 4I over n minus I over n is 3I over n. Be easy to call that 5I over n, but remember you're subtracting each of these two terms. And then I got my I squared over n squared. For consistency's sake, the way I've been doing these is taking this 1 over n and distributing it through the parentheses at this point. So I'll go ahead and do that right now. 1 over n times 2 is just 2 over n. 1 over n times 3I over n is 3I over n squared. And 1 over n times I squared over n squared is I squared over n cubed. Now we can kind of do the 2 steps at one. We can apply the properties of sigma to sort of distribute, loosely speaking, this sigma to each of these 3 terms. And then we can take any constants, anything that don't involve the letter I, and pull them out in front of that sigma. So for this first term, everything's a constant. So let's just pull that 2 over n out in front of the sigma, and we'll leave a 1 as kind of a placeholder. For this second term, the 3 over n squared is a constant because it doesn't involve the letter I. So we'll pull that out in front of the sigma, and we'll be left with just the I. And then for the third term, the I squared is the variable, so 1 over n cubed is the constant. So we can pull that out in front, and we're left with just this. And now comes the stage where we can get rid of all these sigmas. This one and this one correspond to this and this formula. And then the sum from I equals 1 to n of the number 1 is just n, because we're adding up n copies of this number 1. So my first term, I still have the 2 over n, and then this sigma changes into this n. For my second term, I still have the 3 over n squared, but then this sigma changes to n times n plus 1 over 2. Maybe you accidentally memorize these formulas at this point because you've had to use them so many times. And for this last term, the 1 over n cubed stays the same, and then the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Now we need to evaluate this limit, which will be a little bit easier to do if I kind of distribute one more time. 2 over n times n, it just leaves me with 2. And then here I got n squared plus n, and the 3 over 2, not much I can do with that, so I'll just write this as 3 times n squared plus n over 2n squared. think that'll be sufficient for me to figure out the limit in the next step. And then for this last guy, again, not much that we can cancel here. Maybe you have memorized at this point, or you have to FOIL. N squared plus n times 2n plus 1 gives me 2n cubed plus 3n squared plus n. And then down on the bottom, I got the 6n cubed. So evaluating this limit, nothing to do with the 2. It's just a 2. Here, if I divide everything by n squared, this is a 1, this is a 0, this is a 2. So I get 3/2. And here, if I divide everything by n cubed, this is a 2, this is a 0, this is a 0, and this is a 6. So I get 2/6, in other words, 1/3. And these numbers aren't too bad to add up. Let's see, least common denominator would be 6. So I guess I'd call this 12/6, and I could call this 9/6, and I could call this 2/6. Because 12 plus 9 is 21, plus 2 more is 23. So I believe I'm left with 23/6. And then the next topic, a seemingly unrelated topic, deals with antiderivatives here. So I'm given the derivative, and I'm asked to find the antiderivative of some function. So there's kind of two steps going on here. I'm given f prime of x. Maybe my first step is figure out f of x, the antiderivative of this guy. Well, I think it might make your life easier to rewrite f prime of x so that it's in a notation that's a little bit more conducive to using the power rule. Instead of negative 1 over x squared, I could call that negative x to the negative 2 power. And the other two terms are fine, 6x squared and 1. And thinking about it this way, I use the power rule in this first term. So first I look up at this exponent and I add 1 to it. So I get x to the negative 1 power. And then I have to divide by 1 over this number. So kind of 1 over the negative 1. And don't forget, we still have this negative out in front. So there's that negative there. Now for my second term, I want to add 1 to this exponent. So that gives me x cubed. But then I'm not done. I have to divide by this 3 or multiply by the reciprocal of the 3. So that gives this 1/3 here. And then for my 1, you can use the power rule if you really want to. But for most people, they just like, oh, if you have a constant, tack on a variable. So that gets me here. This can certainly be cleaned up. This negative and this negative can cancel out. So I get x to the negative 1 power. And 6 times a third is 6/3, aka 2. So I get 2x cubed here. So here is a prettier looking version of my function f of x, except that I have to remember that anytime I'm taking antiderivatives, there could be a constant, right? Because if I was taking the derivative of this guy plus 7, it would still give me this. So I need to tack on a constant here and tack on a constant here. So now it's a general antiderivative of this function, but I can solve for c because it tells me that f of 1 is equal to 2. So this is telling me that 2 is equal to 1 to the negative 1 power plus 2 times 1 cubed plus 1 plus c. And 1 to the negative 1 power, that might not be obvious. That's the number 1. And that's because when you raise something to the negative 1 power, it just means sort of the reciprocal of that. So it puts the 1 to the positive 1 power down in the denominator. But that's at 1 over 1, which is just 1. So I get 2 equals 1 plus 1 cubed is 1 times 2 is 2. Plus 1 plus c. This looks like 4. Looks like 2. So this must be a negative 2 in order to make things balance. C is equal to negative 2. So what I'm saying is a more specific form of f of x. Instead of using this general form, I could say it's x to the negative 1 plus 2x cubed plus x minus 2, because my constant here I solved for was negative 2. You're like, done? No, unfortunately, we need to find capital F of x. But now we're kind of on a roll. I bet we can do this. Let's see, the antiderivative of this guy. There's one little trick in here. Don't try to use the power rule in this first term. All right, make sure that you recognize that the antiderivative of x to the negative 1 power is the natural log of the absolute value. And then for the rest of the terms, it's just power rule stuff. So add 1 to this exponent. Maybe I'll write it in steps. Leave the 2 alone. X to the 4th power now. But I'm not done. I need a 1/4 down in front. For this exponent of 1, I got to add 1 to that exponent to make it x squared. But then I'm not done. I got to divide it by 2. And then I can tack on the variable to this constant here. And then I'm not done. I need to add on a constant because I'm taking an antiderivative. I'll use the letter D instead of the letter C just to make clear to the reader that I'm not implying they're the same constant. We'll clean this up a little bit before we solve for D. So I get the natural log of the absolute value of x plus 2 times a quarter is 2/4, aka a half of x to the 4th. Not much I can do here. 1/2 x squared minus 2x plus d. So now we'll use the fact that f of 1 equals 10. So 10 is the natural log of this function evaluated at 1. In other words, change all the x's into 1s. That gets me here. It'd be useful if you remember that the natural log of 1 was just 0, because the natural log of, well, the absolute value of 1 is 1, and the natural log of 1 is asking you what power do you got to raise e up to make it equal to 1. Well, e to the 0 power equals 1, so the natural log of 1 is 0. And then 1 to the 4th power is 1, times 1/2 gives me 1/2. 1 squared is 1, times 1/2 gives me 1/2. Minus 2 plus d is supposed to be 10. Well, let's see, here's 1, there's 0, negative 2. Looks like I have 10 equals negative 1 plus d, so d must be equal to 11. So my final answer, capital F of x, a little bit bigger font, I guess because I'm happy to be done, is the natural log of the absolute value of x plus, copying this line here, 1/2 x to the 4th power plus 1/2 x squared minus 2x plus 11, because my constant d here I solved to be equal to 11. If you're the type that likes to check answers, you could take the derivative of this twice and make sure that that gets you back to the original question. But I am not that type, so I'm going to call this good.